Good day, everyone. Today we're going to explore our research work titled On Delay Performance in Mega Satellite Networks with Intersatellite Links, focusing on the potential in enhancing delay performance through the use of intersatellite links. Low Earth orbit satellite networks are becoming increasingly crucial for global connectivity. Projects like OneWeb and Starlink are deploying thousands of satellites aiming to complement terrestrial networks for 5G and beyond. However, constrained by solar power, these satellites require innovative network topologies that are energy conscious without compromising on communication efficiency. This study explores different satellite constellations for long-distance communication in terms of end-to-end delay and robustness to link failures. The study also provides an energy-efficient topology for satellite communication. Low Earth orbit satellites orbit at an altitude of 500 to 2,000 kilometers above Earth. This is in contrast to their geostationary counterparts, which reside much higher. The closer proximity of these LEO satellites to Earth's surface drastically cuts down on latency, paving the way for real-time communications across the globe. The backbone of this emerging network is the innovative use of intersatellite links, enabling satellites to communicate directly with one another. These technologies sidesteps the need for terrestrial infrastructures and diminishing the dependence on ground stations. In our study, we compared two main methods of long-distance communication. Firstly, we compare using satellites, that is depicted by the orange links drawn in the figure in the slide. The formula to calculate the delay using this method is the distance between the leftmost satellite ground station, the leftmost satellite, and then the distance in between the satellites, and the distance between the rightmost satellite and the right ground station. We then divide this by the speed of light, c, and we can also include in this the processing delay, which is the number of hops times by the processing time of each hop. This method was initially proposed by Mark Hanley's landmark paper, Delay is Not an Option. The second method that we compared to is the Great Circle link, which is depicted in yellow. This is the link directly between the leftmost ground station and the rightmost ground station in yellow. And the delay for this is the distance of the link divided by the speed of light, which is divided by the refractive index of the fiber used for that link. We first introduced the nearest hop-based topology, whose goal is to optimize the satellite's network for minimum transmission latency. To achieve this, we create targeted links with the closest neighboring satellites. Through this, a virtual sphere is drawn between each satellite pair. Within the sphere, we apply then a geometric algorithm to determine the most efficient next hop. A next hop is only created if there is no other satellites within this virtual sphere. Once those links are created, we can then use the Dijkstra's algorithm to calculate the shortest path in terms of delay. Each link bears a weight. The weight is the distance to calculate the best path. The energy efficiency for each satellite link is calculated by factoring in the free space path loss. This loss is directly proportional to the square of the link's distance and inversely proportional to the square of the signal's wavelength. Our topology employs a robust algorithm that evaluates potential neighboring satellites within a predefined radius. The goal is to select the most efficient next hop, but by doing so we avoid intermediary satellites that would unnecessarily increase the path loss and ensure an efficient network structure. To further explain, consider a direct link. If the length of the link is doubled, the required transmit power to maintain the signal quality quadruples. This is owing to the free space path loss. This rapid acceleration of power highlights the critical energy efficient approach of the nearest hop topology. And to introduce the cutoff network topology, This is designed with a maximum distance threshold of the intersatellite links, guaranteeing that all connections fall within a distance threshold. We then applied Dijkstra's algorithm, same as before, to calculate the quickest path. The cutoff distance-based topology inherently forms a mesh network, whereby each satellite is connected with every other satellite within the cutoff range. This method maximizes redundancy and paths available for data transmission, which we'll explore further in the coming slides. The dense network topology results from a robust number of connections, scaling by the quadratically as the number of satellites increases. This is shown in the plot on the right-hand side. But however, this leads in a dramatic increase in the complexity of the network management and routing algorithms. Here in this slide, we just show a simulation of the Walker Star constellation near polar orbits, showing how the links are formed and changed as the satellite moves. This link is created from Melbourne, Australia to a point in Europe. To contrast the Walker Star, we also show a simulation of the Walker Delta constellation, so the inclined orbits, also with the same number of satellites, 250, same points as well from Melbourne to Europe. However, for this simulation, we can see that the links change much more sporadically. This sporadic change in length also increases the jitter, or the change in time delay between the two locations. To move on to the results, our results show the number of satellites in a constellation increases, the communication delay through the satellite network decreases, enhancing the efficiency of data transmission. The study also benchmarks satellite delay against traditional Great Circle optical fiber path, highlighting the potential of these satellite constellations to offer reduced latency for long-distance communication. Improvements in delay were observed, particularly over long distances, with the satellite networks approaching or surpassing the performance of optical fiber connection in some scenarios. The nearest top topology, on the other hand, demonstrates a strong delay performance relative to this great circle optical path, while the cutoff distance-based topology shows a slight increase in delay performance due to its more extensive number of connections and its longer length relative to the nearest top topology. We also showed the inclusion of realistic processing delays, which show a marginal impact on the overall delay performance, indicating the efficiency of the hardware plays a significant role. However, further investigation is needed in this area. Next, we compare the delay performance in the Walker constellations, the Walker Star and the Walker Delta. We use 250 satellites in the constellation and compare the delay performance to theoretical great circle optical fiber connections over various distances, similar to the slide before. The same phenomenon is present where the delay performance improvement of the satellite communication system increases relative to the great circle fiber path as the distance between the transmitter and receiver increases. The Walker Star constellation in particular demonstrates lower latency across most measured distances relative to the Walker Delta constellation when using the nearest top topology. The cutoff topology, on the other hand, shows similar performance regardless of the constellation, and again is slightly outperforms the nearest top. So for this slide, we compare the results of real locations showing alternate paths and how these alternate paths show how link failures overall affect network delay. Now, to construct these alternate paths, We systematically remove the optimum path, create a new path in its place. We do this 10 times to create 10 distinct routes between selected city pairs. So for the Walker constellation findings, we find that the Walker Delta constellation displays significant delay variation, suggesting potential vulnerabilities in path diversity. Now, the cutoff algorithm advantage in this is shown it's quite robust to link failures, where a much higher amount of links are created. Therefore, the delay variation isn't too high. Now, if we compare this to optical fiber, we can see that terrestrial optical fiber tends to outperform the satellite network if the distances between the cities are quite low, for example, Melbourne to Sydney. However, the alternate is shown when observing city pairs that are very far apart. For example, on the far right, we see the Perth to the France link. So we can see that the satellite tends to outperform the optical fiber link. Now, just to summarize, our analysis highlighted the balance between delay performance and the robustness to link failures. Our proposed nearest hop topology demonstrated strong delay performance compared to traditional optical fiber connection. The comparison between the two Walker constellations, the Walker Delta and the Walker Star constellations, revealed distinct trade-offs, with the latter providing lower latency and a lower level of jitter. Investigation into network robustness showed the cutoff distance-based topology presented a resilient structure against link failures, suggesting its suitability for critical applications. Moving forward, incorporating a dynamic routing algorithm and machine learning could further optimize constellation topologies, adapting in real time to changing network conditions and traffic demands.